Hello there, you're listening to the Science of Everything podcast, episode 110, Weather Part 2. I'm your host, James Fodor. So, in this second in our two-part series on the weather, we're going to be continuing from where we left off last time, which was talking about air masses, and begin by talking about fronts, which then allow us to understand the formation of storms and other weather phenomena in mid-latitude. So, we'll talk about mid-latitude cyclones and then move towards the more well-known tropical cyclones, and finish off by talking about thunderstorms and also tornadoes. The recommended pre-listening for this episode is, not surprisingly, the previous part, episode 109, Weather Part 1. And I'll be using concepts introduced in that, so make sure you've given that a listen before listening to this one in order for everything to make sense. So let's jump straight in then and start talking about weather fronts. Remember from the previous episode where we talked about air masses, an air mass being a large region of air that has similar properties. So particularly we're talking about properties of whether it's moist or dry, that is whether it is relatively saturated with moisture or relatively unsaturated, and also temperature, so whether it's basically warm or cool. Warmer air coming from closer to the equator and cooler air from the polar regions. Now, what happens when different air masses come together? Well, in that case, you have the formation of what is called a front. The language of fronts actually comes from the First World War, where you had, armies from the Central Powers and the Allies lined up along big fronts, which you could mark with, lines on the map. And that's actually the origin of the name for weather fronts. And it's a sort of similar idea. If you think of the air masses as representing competing armies and the boundaries between them where they sort of clash together as the front, then you have some idea of the basic structure of how it fits together. So a weather front is just the boundary that separates two air masses of different densities, and air fronts are the principal cause of most weather phenomena, including storms and precipitation and so forth. So generally what happens is when one air mass moves into or sort of pushes against another, they generally don't mix. I mean, if they did mix, then they wouldn't really be air masses anymore, because the whole definition of an air mass is a large volume or region of air that maintains consistent properties distinct from its surroundings. So I guess if the air masses start to mix, then they cease to be distinct air masses. But usually that doesn't happen. Usually what happens is one mass displaces the other with a boundary of a few kilometers on either side across the front, which is quite narrow if you think about air masses as usually being hundreds of kilometers or even thousands of kilometers across. So they are fairly well defined in the scheme of things. Because warm air is less dense than cool air, warm air masses always lie over the top of cooler air masses. There are two main types of fronts that we'll talk about here, cold fronts and warm fronts, unsurprisingly. The cold front is named after the situation when a cold air mass moves into or displaces an existing warm air mass. So think of the warm air mass as being stationary, the cold air mass is coming in and pushing it out of the way. A warm front is the other way around. The cold air mass is stationary and the warm air mass comes across and begins to displace the existing cold air mass. So the fronts are named after the mass that's coming in and pushing the other one out of the way. Cold fronts and warm fronts have different shapes because of the different properties of cold compared to warm air. In particular, a cold front is much more kind of squashed, particularly near the ground level. And the reason for that is because, as we've just explained, cold air masses are denser and so always sit closer to the ground. And therefore, as they're moving along the ground, they experience more friction with the ground, which kind of slows it up, especially near the front, where it's most in contact with the ground. So you can think of a cold air mass as kind of like the front of a bullet train. It's kind of elongated, but kind of also rounded off a bit at the front as it's compressed at the lowest part of the closest to the ground by friction as it moves forward. By contrast, warm fronts are have a much shallower slope because the warm air is moving across on the top of the cold air and therefore has much less friction with the ground. Obviously, there's friction when the warm air is in direct contact with the ground, but as it moves up over the cold air mass, that friction diminishes. And so the slope is shallower and the warm air rises. The incoming warm air mass rises above the cold air much more slowly in comparison to the warm air that's pushed up above the cold air mass, because the cold air mass is like a freight train sort of pushing through, and because it has a steeper slope, it pushes the warm air up above it very rapidly, which causes the air to rapidly ascend, and that gives rise to vertically structured clouds and sometimes storms, because the air is being pushed up very rapidly, and therefore the any moisture in the air will precipitate out and form clouds, which have vertical structure because the air's moving up so quickly. That doesn't tend to happen in warm air masses because the clouds form much more slowly because the warm air is being moved up to higher and higher altitudes more gradually due to the shallower slope. And therefore, at warm fronts, you tend to have much less vertical cloud development. Instead, you have horizontally stratified clouds like cirrus clouds. Precipitation can occur at warm fronts, but it's generally over a wider area because of the more slow, the shallower slope and the more gradual ascent, and more gentle because the whole process of the rising and cooling of the air occurs more gradually. So you get less precipitation in one place very rapidly. So basically, the long and short of that is that because cold air sits close to the ground, it moves more slowly into the warm air mass. That means when it does move in, it pushes the warm air up very quickly. That causes it to rise quickly, moisture to precipitate out, and causes storms and vertically stratified clouds. Whereas in the warm fronts, the warm air moves above the cold air, moves gradually and slowly across it, therefore uplift is slower, precipitation occurs, but it is much more diffuse and spread out, and you don't tend to get vertically stratified clouds. So those are the two main types of fronts. There's also such thing as a stationary front. That's when you have a cold and an air mass that are kind of next to each other, but neither is moving into the other. And because either could move into the other or something could change, stationary fronts tend to be quite unpredictable in terms of what weather will be occurring. And there's another type of front called an occluded front, which we'll talk about in a moment because it's directly related to cyclone. We'll talk about that more in a moment. That leads us on then to mid-latitude cyclones. In ordinary conversation, when people talk about cyclones, also known as hurricanes or typhoons, and there are other regional names as well, people tend to think about tropical cyclones, which occur, as the name indicates, in the tropics, or at least are formed in them. But in meteorology, a cyclone is just any large-scale air mass that is rotating around an area, a central area of low pressure. An anticyclone is the opposite in the sense that it's a large-scale air mass that rotates around a center of high pressure. Because low pressure cyclones are the main cause of weather phenomena, I'll be focusing on them rather than anticyclones, but be aware that they exist as well. Mid-latitude cyclones are those that occur in mid-latitude, so basically outside of the tropics, but also outside of the polar regions. And then tropical cyclones form in tropical areas. They're both similar in the sense that they're formed as a result of air rotating around low pressure systems, and they give rise to storms and unstable weather conditions, but they're different in the details and also how they form and the regions that they form in and so forth. So we'll talk about them separately. Also, I'm generally going to be focusing on a northern hemisphere analysis just because that's where more people live and more sources tend to focus on. The general principles are similar, but things tend to be kind of opposite in the southern hemisphere. In particular, the Coriolis effect, which, remember, is the effect of apparent motion or rotation of air as a result of the rotation of the Earth, causes wind flow around cyclones to be counterclockwise in the northern hemisphere and then clockwise in the southern hemisphere. So mid-latitude cyclones, as I said, they're low-pressure areas with the air rotating around them, sort of spiraling inwards, basically, because you have low pressure. That means that there's lower pressure of air, so air is going to tend to move in towards the low pressure, and that occurs not directly, but in a sort of rotational manner, partly because of the Coriolis effects, but also due to other forces that we'll talk about in a moment. Extratropical cyclones or mid-latitude cyclones are capable of producing anything from sort of just clouds up through to heavy thunderstorms, gales, blizzards, and even tornadoes. So they're the cause of a lot of sort of more extreme weather phenomena in mid-latitude regions. As I said, mid-latitude cyclones form outside of the tropics, so that's basically 30 degrees or more away from the equator, but also outside the polar region. So basically this is 30 to 60 degrees away from the equator. Now, mid-latitude cyclones can form in a variety of circumstances, and the details are not always completely understood. But I'm just going to present a general outline of the sort of key stages in the process of how they form and how they develop. So the basic idea is that mid-latitude cyclones begin as a stationary front. So remember, that's when you have a cold air mass and a warm air mass next to each other, not moving into each other. That doesn't mean that the air is not moving, but it may mean that the air is moving sort of parallel to the front boundary, or to the front separating the two air masses. And that happens in a number of regions on the Earth's surface. In particular, it happens around the boundary between the atmospheric circulation cells, which are the large circulation cells of air that move warm air from the equator up to the roughly 30-degree latitude regions, and then there the warm air is moved from the 30-degree edge of the tropical regions up to the edge of the polar region, and then the polar cell brings cold air from the poles down to the edge of the mid-latitude cell. So it's particularly at the boundary between the polar cell and the mid-latitude cell where you have masses of air of different temperatures moving parallel to each other that front formation is particularly common. Now, in that situation, that can give rise to a cyclone if certain things occur. And in particular, the key to any type of cyclone, but also including a mid-latitude cyclone, is that there has to be a central low pressure region that the surrounding air tries to sort of move inwards towards to fill up that low pressure. Now, how does that low pressure form? Well, there's many different ways it can form. One way is if you start with the stationary front and it begins to sort of, instead of being a relatively straight line, it begins to sort of meander back and forth, having a wave-like appearance. If this happens, then some of the regions where the air is moving away from, so it's sort of wobbling backwards and forwards, can become relatively low-pressure regions, whereas other parts of it can be more high-pressure regions, as the kind of like a stream meandering backwards and forwards. If the stream is sort of bending towards the left, then the side of the river that it's sort of bending towards will experience a greater force of the water pushing on that side, causing erosion, whereas the side away from which the stream is bending will experience relatively less force, and thereby you tend to get deposition on that side. That's not exactly the same phenomenon, but it's kind of vaguely similar in the sense that you can get a change in the pressure on sort of one side to the other when you get this sort of wave-like behavior. And that can be one mechanism by which these low pressure regions form. They can also form as a result of the effect of geographical barriers, such as perhaps there's a mountain range that causes orographic lift, causing the air to move upwards and potentially causing a low pressure zone around the mountain area. And there's many complicated effects that can contribute to the formation of the low pressure zone. But however exactly it forms, as the fronts sort of meander relative to each other and a low pressure zone forms in one part of that front, then instead of being stationary relative to each other, the cold and the warm front, they then begin to move sort of inwards in towards each other, trying to basically move inwards to fill the low pressure zone. As mentioned before, they don't do that directly because of the Coriolis effect. They sort of curve and bend aroundwards. And then you can sort of see as they're curving towards the low pressure zone, you begin to have the beginnings of a mid-latitude cyclone with the low pressure and the air rotating surrounding it and spiraling inwards towards the low pressure zone. Once this process has begun, it sort of takes on a life of its own. So the cold air mass, which originates generally from the polar regions, will then begin to move equatorward because it's moving towards it's sort of trying to get to the low pressure zone, but it's also moving into the warmer regions of air that are close to the equator. Conversely, the warm front is going to move towards the pole, rotating around, but also moving from the warmer region into the colder region. So you've got now, instead of a stationary front, you've got a cold front and a warm front. And the way it tends to work out is that if you imagine a sort of a horizontal line with the cold air mass on the top and the warm air mass on the bottom, initially they're just kind of sitting there or moving parallel with respect to the front. But when the low develops, which you can think of as developing the low as forms a kind of a hinge, then at that low hinge, the cold front begins to sort of rotate downwards around and gradually catches up to the warm front, which is on the other side of the hinge. So if you kind of put your hands in front of yourself and direct your fingers in towards each other, sort of like you're forming the ground as a flat surface in front of you, and then rotate your left hand downwards, keeping the middle fingers of your two hands attached, but forming a hinge and sort of rotating around, bringing your palms together. That's kind of what's happening in the development of the tropical cyclone. You've got the cold air mass on top. The cold front forms as the cold air mass moves into the warm air mass, and the warm front forms as the warm air mass moves upwards into the cold front. The thing about this is that the cold and warm fronts don't move at the same speed. The cold air, which forms the cold front, moves more rapidly than the warm air forming the warm front. The reason for this is because warm air is less dense, therefore it's easier to push out of the way. So the cold front is sort of barreling through the warm air, moving towards the equator, but also kind of around, spiraling inwards towards the low pressure zone. The warm front is doing the opposite. It's sort of rotating upwards. That is, well, upwards in our sort of diagram, but more generally towards the pole and rotating inwards around to the low pressure zone. But the cold front is gradually catching up to the warm front because it's pushing the warm air out of the way more rapidly than the warm air is able to push the cold air out of the way in the warm front. Eventually, the cold front will catch up to the warm front, and when this occurs, it forms what's called an occluded front. So this is what I mentioned before. It's when the cold front has sort of caught up to the warm front. When this happens, the warm air is entirely cut off from the surface of the Earth, in that particular location, because you've basically got a situation in which you've got a warm front, which is warm air moving into cold air. So the warm air is moving on top of the cold air, as we mentioned. And the warm air will initially still be in contact with the ground, except until it gets kind of caught up by the cold front moving from behind, which is pushing the warm air out of the way. Eventually, when the cold front catches up to the warm front, the warm air mass loses all contact with the ground, and that's what is called an occluded front. Occluded fronts, when they form, that represents a phase in the development of cyclones called cyclolysis, which basically represents the end of a cyclone, when the low pressure system in the middle loses contact with the warm air that provides the energy essentially for the cyclone to occur, because now once the cold front's caught up to the warm front, the low pressure system's entirely surrounded by cold air. The warm air's being pushed away from it, at least at the surface of the Earth. That thereby removes the source of energy, the underlying source of energy, which is warmer air, which has more energy than the colder air. The source of energy is removed, and thereby the cyclone eventually sort of peters out. This whole process, from the initial sort of waviness along the stationary front to the formation of a low pressure zone, which then gives rise to the cold and the warm fronts, the cold front rotating like a pivot, barreling around and catching up to the warm front, forming an occluded front, and then cyclolysis, ending the cyclone, typically takes about a week. So they're not terribly long-lived. And during the process, they can give rise to a wide range of weather phenomena. In particular, as we discussed before, at the cold front, you typically have rapid upwelling of air, of warm air in particular, which will then produce vertically stratified clouds, which tend to condense moisture rapidly and cause a lot of rain, and also wind action as you have the air masses moving into each other and the pressure differential into the low pressure zone. So this is where you tend to get precipitation, thunderstorms, blustery winds, etc. Let's move on now from the mid-latitude cyclones and talk about tropical cyclones, their more famous cousins. So as I mentioned before, these occur in tropical regions, so between roughly sort of 30 degrees latitude of the equator, although they can move across that line. The formation of tropical cyclones is similar to mid-latitude cyclones, still not completely understood, and therefore I'll just give a general outline of how it all works. One of the key differences between a mid-latitude cyclone and a tropical cyclone is that tropical cyclones are much more symmetrical. So you remember in the case of the mid-latitude cyclone, you've got the cold front and the warm front, and the cold front sort of is rotating around, catching up to the warm front as the cold air mass displaces the warm air mass. So there's sort of different sides to a mid-latitude cyclone. That's not the case for a tropical cyclone, because unlike mid-latitude cyclones, they don't form at the boundary between hot and cold air masses, or at least warm and cold air masses. Rather, they form in the tropics, where essentially all the air is warm. So tropical cyclones are much more symmetrical. One similarity with mid-latitude cyclones is that tropical cyclones also generally appear to grow from perturbations or meanderings of existing wind patterns, although in this case it's typically the trade winds, which are easterly winds, so they're winds that start from the east and blow towards the west, and these are the prevailing surface winds in the tropical regions around the equator, roughly 30 degrees other side of the equator. Perturbations in these wind patterns can give rise to low pressure zones, which can form the basis or the sort of the nexus of formation of a tropical cyclone. It's interesting that if you look at a map of tropical cyclone formation, you'll see that they always form in tropical regions, but they never form right at the equator. They have to form at least a few degrees north or south of the equator. And the reason for this appears to be that you need enough of a Coriolis effect in order to get the rotation that's necessary for the cyclone to exist, because it's rotated, the air sort of spiraling inwards around a central low pressure system. And because there's no Coriolis effect at the equator itself, then rotation is not available and you can't get cyclone formation there. Another requirement for tropical cyclone formation is sufficient energy, and that energy fundamentally it's derived from the release of energy by the condensation of moisture in the humid air as it rises up, cools down, the moisture condenses and releases that energy. So it's basically coming from the fact that oceans are warmed and a lot of the water evaporates, causing the air to become saturated or nearly saturated around the surface of the oceans in the tropical regions, obviously owing to the sunlight, the higher intensity of sunlight in that area. The reason you tend to get such high wind speeds, or at least you can get very high wind speeds in tropical cyclones, is because of the fact that the whole air system, which can be hundreds or in extreme cases thousands of kilometers across, is rotating about a single low pressure system. And it has a symmetry that, as I said, mid-latitude cyclones tend not to have. And so therefore, you tend to see more impressive sort of spiral cloud formations from tropical cyclones. But also because of that, as the radius of rotation contracts downwards as the air gradually moves closer to the center, the angular momentum must be conserved. And as we know from previous episodes, conservation of angular momentum means that as you move closer to the axis about which the rotation is occurring, the speed relative to the center, sort of the radial speed, increases to conserve the angular momentum. And that's why you can have, particularly near the center of the storm, extremely high wind speeds, because of that, basically the rotation has been compressed to that smaller space. The structure of tropical cyclones, however, is a bit more complicated than that. It's certainly not just a sort of spiral of air moving inwards towards the low pressure zone. In fact, many people know that the tropical cyclone has an eye of the storm, as it's often called. This is a central region called also the central depression, in which there is relatively low wind speeds and no clouds. So in fact, there's really cool images from satellites of people, of photos taken looking down right into the eye of a storm, of the tropical hurricanes, and seeing the surface beneath, because there's no clouds there. The reason for this is because remember that clouds form, particularly we're talking here about vertically stratified clouds. They occur when there's relatively rapid uplift of moist air. Then as the air is being uplifted, it cools. There is condensation of the moisture that was in that air, and that forms clouds. And if there's sufficient condensation, it can give rise to precipitation. The lack of clouds in the center of a tropical cyclone is indicative of the fact that in the very center, or in the eye region, air is actually not uplifting, it's actually going downwards. It's going down from the top of the storm towards the surface of the Earth. And this region is relatively warm. I don't know if it's fully understood exactly why this happens in the way that it does, but it is known that what you sort of have is around the center of the eye is where the air is being uplifted, producing the clouds, and sort of spiraling upwards around as the air from around the outside is moving into the low pressure zone. And then because it's all moving towards the same central area, it sort of pushes upwards, moves, and the moisture condenses out of the air as it cools and thereby forms the cloud structure. The very middle, however, in between this sort of funnel of spiraling and uprising air, actually is moving downwards in the opposite direction, causing that central depression and causing the lack of clouds there because the air is moving downwards, and so you don't get this condensation. Tropical cyclones are a positive feedback cycle. So what happens is the air moves inwards and sort of eventually reaches the center where it spirals up around the central depression zone. Once it reaches the top of that central region, it's pushed outwards by the air that's coming inwards behind it, moves radially outwards away from the center of the storm, but now at a higher altitude, a few kilometers up in the atmosphere. And eventually, once it's moved further away from the storm, it falls again and then reaches the surface and is pulled inwards, or I guess pushed inwards, pulled inwards by the low pressure zone at the center. So it's all one big circulation. It moves along the surface towards the low pressure zone, is pushed up around the sort of as a funnel, spiraling upwards around the center or the eye of the storm. Once it reaches the top, it is pushed outwards away from the storm, and then once it's moved sort of away from the cloud, the central region, it falls again and then is pulled back inwards across the surface, picks up energy also as it moves across the surface of the ocean. It will regain the moisture that it lost when it was being upraised. It should regain that moisture from the hot tropical ocean surface, and then it will rise up again. So it's a big cycle occurring sort of radially around all sides of the center of the storm. And this positive feedback mechanism allows the hurricane to continue and to sort of move as a single unit. The eye of a tropical cyclone is typically about 50 kilometers across. Usually it's right at the center. And as I said, there are no clouds there because there is no or very little air that's moving upwards in that region, but the air tends to move downwards. So you don't get the vertical cloud formation. Hurricane or cyclone wind speeds can range from about 100 kilometers up to, in extreme cases, 300 or so kilometers per hour. Now, this compares to sort of mild breeze wind speeds that are about 10 or 15 kilometers an hour. So you can see that they can be extremely damaging. Notwithstanding, though, the greatest damage of tropical cyclones is not generally caused by the intense wind speeds, but by the flooding that they produce, at least when they reach land, which is called landfall. When this happens, you have an effect called the storm surge, which is quite complicated, and I don't want to get into all the details of why that occurs, but it seems to be a combination of the effects of rain brought by the cyclone and wind pushing the water basically up towards land, and also the low pressure brought by the low pressure zone, which essentially causes the water to move up higher than it would otherwise be. So these and some other effects all cause a surge, which basically means the water moves up, the water level rises, and can cause massive flooding in areas that are near the coastline, or even not so near the coastline sometimes, depending on how flat the land is. So that tends to cause the most damage and the most deaths in cyclones, not the wind itself. Tropical cyclones are named, as you probably heard, they're given names of just first names of men or women. The reason that they're named is so as to avoid confusion when communicating to the public, as you can have multiple tropical cyclones existing at different times, and they also obviously exist over a wide area. So it's useful to be able to refer to specific storms in a clear and easy way, and therefore names are used for that purpose. This procedure was begun, I think, after the Second World War in the US, and has sort of been adopted by other countries as well. The names are drawn from predetermined lists for a particular year, and so they just go down the list, naming the first cyclone of the year after the first name, and then so on and so forth. And the names are changed, I think, yearly these days. They used to be changed every few years, but when you have a very damaging storm that causes a lot of loss of life, then they are removed from the list and not used in the future. The path of cyclones, tropical cyclones, is interesting. As I mentioned before, you can see maps of the trajectories of tropical cyclones across most of the oceans, and also sometimes as they reach landfall. Remember that tropical cyclones always occur over the ocean, because that's where you have the high energy, warm, moist air that's necessary. They always occur within a few degrees away of the equator, but still within the tropical zone. Once they form, they pretty much always move towards the west. That's because of the easterly trade winds, remember, which are the prevailing surface winds in the equatorial region. So they push the cyclones to the west, and also tend to move away from the equator, as essentially they're moving towards cooler air regions. This results in eventually them, at least they can, I mean, sometimes the cyclone will peter out before it reaches this stage, but if they travel far enough, the cyclones can cross the 30-degree boundaries, at which point the trade winds subside and are replaced by westerlies, which are, as the name indicates, winds where the air comes from the west and blows towards the east. Remember, winds are always named after the direction that they're blowing from. So around 30 degrees away from the equator, the trade winds are replaced by the westerlies, which blow in the opposite direction. And therefore, you see this sort of curve pattern where in either hemisphere, the cyclones first move towards the west, and then once they reach a certain high enough latitude, either north or south of the equator, then they curve back and move back in the opposite direction. That's basically because they're being blown in the opposite direction now by the westerly winds. And you can see these patterns very consistently in the maps of the cyclone trajectories. Now, these patterns and also the location of the formation of the cyclones give rise to very predictable and, well, at least over long periods of time, quite predictable patterns of where they tend to occur. Most tropical cyclones mostly form in the Pacific and Indian Oceans. There are also some that occur in the North Atlantic Ocean. There are hotspots of formation that are kind of off the Atlantic coast of Mexico, both in the sort of central Pacific region, and also more sort of southerly, sort of north of South America and northwest of Africa. There are tropical cyclones that form and then move into to the Caribbean and then can curve back and up and cross the east coast or just off the east coast of the US. So that's where most of the hurricanes that hit the US come from, is basically the middle of the Atlantic Ocean, moving, sort of curving around, coming to landfall often around Florida or maybe a bit west of that, and then curving backwards across the east coast. It's almost like that it was designed to sort of hit as much of the US as possible, at least for some of them, if they hit landfall in just the right place, because they'll curve backwards just along the heavily populated coastal area. But of course, that's just coincidence of the way the landmass is shaped. There are also many cyclones that form in the sort of central Pacific area, a few degrees to the north of the equator, and many of those will then curve towards the west and make landfall sometimes in the Philippines, sometimes in Japan, sometimes in China, and then sort of curve northwards and then eventually eastwards away. Tropical cyclones always dissipate within a few days generally of making landfall, because once they do so, they're cut off from the source of energy, which, recall, is the warm, moist air overlying the tropical ocean regions. And so they can't sustain themselves for very long over the land, but they can still last a few days away from their source. Finally, there are other cyclones that occur in the southern part of the Pacific Ocean and also the Indian Ocean, and those tend to make landfall either on the east coast of Africa or sometimes on various parts of the northern coasts of Australia and also some of the islands around there. Interestingly, there are essentially no tropical cyclones that form off the coast of South America, either in the South Atlantic or in the eastern part of the South Pacific Ocean. The reason for that appears to be the nature of the ocean currents that operate in that area, which give rise to much cooler surface water than exists in the other regions of the ocean. Thereby, the surface of the ocean is not sufficiently warm to provide enough energy to sustain a tropical cyclone. So you might predict that you would have a lot of cyclones hitting, say, Brazil, but in fact they essentially never get tropical cyclones because the water there appears to be too cold. Let's now move on from tropical cyclones and talk a bit about thunderstorms. A thunderstorm, also known as a lightning or an electrical storm, is a storm that is characterized by the presence of lightning and its acoustic effect, which is called thunder. So I'm sure everyone knows that lightning is produced by the separation of electric charge within a cloud, so that you have a charge region near the base of the cloud, which then, once it reaches a certain threshold, equalizes or sort of discharges with the ground by ejecting a bolt of lightning. There are many different types of lightning, and exactly how they form is quite complicated. So I want to focus here more on the weather aspect than the electrical aspects. But just as people probably know that the charge separation gives rise to the electrical phenomena of lightning, which then equalizes the charges, the acoustic effect that we hear as a result of that is known as thunder. So thunder always occurs after lightning because it takes time for the sound to travel, and if you are good at sort of measuring time, you can count how long after you see the lightning you observe you hear the thunder, and that gives you an idea of how far away the lightning occurred. Of course, it can be difficult sometimes to isolate whether a particular thunderclap is due to a particular bolt of lightning. If you have an electrical storm with a fair bit of lightning, and sometimes you have lightning that goes from one point in the cloud to another point in the cloud, and so you don't see a bolt that's visible on the surface, and it can be a little hard to trace exactly what belongs to what. But anyway, that's what gives rise to those phenomena. The charge differential itself, which is equalized eventually by lightning bolts, is the result of friction, essentially, between the movement of air and carrying moisture with it as it moves in the cloud that gives rise to the thunderstorm. So thunderstorms usually occur in highly vertically stratified clouds. So if you recall back in the previous episode where we talked about the different types of clouds, I didn't say that much about the vertically stratified clouds because I wanted to talk about them more in this episode when we discussed weather in more detail, because it's these types of clouds that give rise to most of the weather phenomenon that we're familiar with, in particular thunderstorms. The most common and well-known type of vertically stratified cloud that we're going to focus on here are the cumulonimbus clouds. And these are sort of the classic thunderclouds that have a towering vertical extent, and at the very top often form a sort of an anvil shape with a flat surface. That flat top occurs as a result of the vertically moving air eventually reaching the top of the troposphere, at which point the troposphere gives way to the stratosphere, and there's a temperature inversion that occurs around that altitude of around 10 kilometers. The temperature inversion means that the air cannot keep rising, or it's at least very difficult for it to keep rising, and so it tends to be pushed outwards either side, giving rise to that sort of flat top that's characteristic of these clouds. And because you have rapid vertical uplift of air, you get, of course, cooling of the air, which gives rise to condensation and therefore precipitation. So cumulonimbus clouds and thunderstorms that go with them are associated with large amounts of precipitation. Now, I've already mentioned before that the uplift of air, the rapid uplift of warm air, in particular warm moist air, can be caused by a variety of factors. It can be caused just by the extensive solar irradiation of particular regions of the surface of the Earth, especially over the ocean, which gives rise to warm and moist air, which then will move upwards, cooling, precipitating, and then giving rise to, in some cases, cumulonimbus clouds and thunderstorms. But this can also occur as a result of the convergence of air moving across the surface into each other. So an example of that would be a subtropical cyclone, when you have the cold and the warm fronts with the air masses colliding with each other. Or you could have orographic lifting, where the terrain forces the air upwards and then causing precipitation. So any of these or other mechanisms can cause cumulonimbus clouds to form. As the water vapor precipitates and then forms with sufficient condensation nuclei, the condensation droplets will form into water droplets or ice, depending on the temperature, and if they reach a sufficient mass, they'll fall to the Earth. And as they do so, they drag some of the air with them, generally colder air from a higher altitude. And that air, as it moves towards the Earth's surface, produces a downdraft, which can then spread out over the Earth's surface, causing strong, cold winds that are often associated with thunderstorms. So that's basically air that's been brought with the rain or with the hail or snow, depending on the situation. Once a thunderstorm has been disconnected from its source of energy or has dissipated its energy in another way, then the uplift of the warm, moist air is dominated, begins to recede in importance or in magnitude, and is dominated by instead the downdraft of cool air coming downwards. This will essentially push down the thunderstorm, hitting the ground, spreading out, and further cutting it off from whatever warm air was being pulled up into the thunderstorm, and thereby essentially dissipating the storm. This can happen relatively quickly, within only 30 minutes or maybe a couple of hours of the formation. So thunderstorms aren't nearly as long-lasting as cyclones are, which tend to last on the order of days or to a couple of weeks. The final weather phenomena that I wanted to discuss in this series are tornadoes, which are obviously especially fascinating and also frightening atmospheric phenomena, and something you just really wouldn't naively predict if you didn't know that much about weather, as most people don't, as to how this very focused, relatively small, rotating mass of air is able to form. And there's still much that is not known about the formation of tornadoes. So again, I'll just give a brief outline of some of the basic concepts. And before we talk about tornadoes, I need to introduce the concept of a supercell. So a supercell is really just a storm, but it's a particularly large, unusually severe storm. And it typically occurs when you have a situation in which wind speed, or sometimes wind direction as well, varies with height. This is called wind shear. So the speed of the wind varies with the height above the ground, and therefore you have a shearing effect. This in turn produces sort of a spinning effect, where you get sort of rolls of air that are sort of spinning around, with the roll being, you imagine like rolling a sausage, it's sitting horizontally on top of the surface of the Earth. So because you've got, say, the stronger air at a higher altitude and the weaker air at a lower altitude, it's sort of the spinning rolls of air are rotating like as if you were rolling the sausage along the ground. So this is different from other phenomena that we talked about before, like the air that spirals upwards around the central region of a cyclone, where the air is rotating and spiraling upwards. This is the spirals that exists because of wind shear. Now, this will eventually give rise to, or can eventually give rise to, tornadoes. But one of the issues at present is essentially the tornado is pointing in the wrong direction. We know that tornadoes are essentially a vertical phenomena, where you have a rotating column of air that is vertically oriented relative to the ground, whereas these spinning axes of air are horizontal relative to the ground. So how do you get this sort of rotation? How does the rotating air go from being sort of horizontal to vertical? And the answer to that is updrafts of air. And we know that these occur in thunderstorms or in supercells in particular because we just discussed that. You have the moist, warm air that moves inwards and then upwards. As it does, it cools and precipitates, and any air that is in that region will be pushed upwards by the updraft as long as the updraft is strong enough. And in supercells, you have, as I said, sufficiently large movement of air and sufficiently energetic updrafts so that you can basically bend or rotate this spinning air so that instead of your sort of sausage rolling around horizontally, it begins to bend upwards as if it was standing on its end. And this is called a mesocycle when that sort of rolling air caused by the wind shear moves from being sort of horizontal to upwards. That's a mesocycle. It exists sort of within the thunderstorm, inside the cumulonimbus cloud typically. Supercells nearly always cause very severe weather, including tornadoes, although supercells don't always lead to tornadoes. But because they're so energetic, the weather they cause is usually very severe and can give rise to very large hailstones up to 10 centimeters in diameter, which is pretty crazy, and winds in excess of 130 kilometers an hour, which is not as severe as tropical cyclones can get, but is still obviously very, very large. The mesocyclone is not the same as a tornado. The mesocyclone is essentially what gives rise directly to the tornado. A tornado itself is defined as a violently rotating column of air which is in contact with the ground, generally from sort of extending from a cumuliform cloud or just underneath it. In particular, a tornado doesn't have to be visible. The part of the tornado that's visible is called the funnel, and that is typically quite narrow, perhaps a few hundred meters, or in extreme cases, a kilometer or more across. So that's still fairly large compared to a person, but very small in comparison to the size of these storms that they form from. But as I mentioned, the funnel itself is not the same thing as the tornado, which I think is slightly different from common usage, where you generally wouldn't say there's a tornado unless you saw the funnel itself. The funnel is not really the tornado. What you're seeing is condensation, dust and debris that's being pulled into the tornado and is circling around and makes it visible. But not all tornadoes are visible that way. So you can have the rapidly rotating column of air, but it not be visible or very hard to see. And therefore, it wouldn't have a well-defined funnel, but it would still be a tornado. Basically, the actual making contact of the ground phase of the formation of a tornado occurs when the rotating mesocycle is pulled downwards, generally by the formation of a low pressure zone right at the surface of the Earth due to all the updraft of the air that's moving upwards and then fueling the supercell. That can pull the mesocyclone down and cause it to make contact with the Earth. Tornadoes typically don't last for very long, usually only a few minutes, but they can be extremely dangerous when they do so. The severity of tornadoes is measured by what's called the enhanced Fujita scale. The old Fujita scale, which measured from F0 to F5, has been replaced fairly recently, 2007, by the enhanced Fujita scale, which goes from EF0 through to EF5, which are the most damaging tornadoes. Most tornadoes are of EF0 or 1 and are not especially damaging, although they can still cause damage. The types of tornadoes that can really completely destroy or level structures are the EF3 and above, especially 4 and 5, which are extremely devastating. These type of very intense tornadoes are very rare. Well, they're very rare in general, but they're extremely rare, especially outside of anywhere except for particular parts of the US. People have probably heard of a region called Tornado Alley, which is not very well defined, but it's sort of a general region around parts of the southern states up through to some of the Midwest states, which have particularly large and unusually large by world standards numbers of tornadoes. Tornadoes do occur in many parts of the world, mostly in temperate regions. They're fairly rare in tropical regions, but they're most common of all in the US, particularly those regions of the US that I just mentioned. Just to recap, so the basic idea of how they form is you have different wind speeds at different altitudes, which causes a sort of rotating axis of air, like I described as a sausage sort of rotating horizontally relative to the Earth. Then extreme updrafts, rapid updrafts of air that are being pulled upwards as a result of different forces that can give rise to a thunderstorm or cumulonimbus clouds can essentially bend and rotate those spinning mass of air so that they become vertical, forming what's called a mesocyclone, which exists in sort of the center of some very intense thunderstorms, which are called supercells. Sometimes, in the right circumstances, these supercells can form a very low pressure zone around the base of the cloud, particularly as a result of very rapid updrafts of air, which then kind of pulls the mesocyclone down slightly, allowing it to make contact with the Earth and forming a tornado, which is in some cases visible as a result of particulate matter and dust and debris and so forth. And that visible part of it is called the funnel, although the tornado itself is the whole rotating mass of air. So that concludes our second part of this episode and also our series on weather. I hope that you found it entertaining and informative. Obviously, we only provided a brief introduction to all of these phenomena. There's much more that can be said, and I think we may well revisit some of these in more detail in future episodes. But if you enjoyed this, consider supporting the podcast by leaving a review on iTunes or your podcast aggregator of preference. You can also send me questions, suggestions, or other feedback. If you want to send me an email, my address is fods12@gmail.com. That's fods12@gmail.com. If you would like to support the show financially, you can make a one-off donation via PayPal or become a Patreon supporter if you just go to the links that should be in the video description, or you can just Google Science of Everything Patreon. You'll be able to find that. I appreciate all of my generous donors, and that helps me to spend more time on the show and get more quality content out to you guys. So that's all for today. Thanks again for listening, and I'll talk to you next time.